Last one for this week. So, de Moivre's theorem is about finding, raising these complex numbers to a power. So if I just do the product rule with itself several times, I'll have like r times r times r, however many times I'm multiplying. I'd have theta plus theta, however many times I'm multiplying them, so n of them. So that's where our power comes from. All right, so 1 plus I to the 5th. So there is the ugly way. I cheated and pulled these numbers from Pascal's triangle because it was a 1 and 1. So, like, that's what would it be if you like FOILed out all 5 of those together. And then our i's actually are equal. I squared is -1. So I cubed is -1 times I. I to the 4th would be -1 times -1. So it's just 1. And then I to the 5th, I to the 4th times I. So the I to the 4th becomes a 1. So just an I. And then we can combine our terms and get our answer. Also, we can use de Moivre's theorem. So if we convert this into polar notation, so let's just think real quick about where this point is. 1, 1. So 1 squared plus 1 squared is 2. So our radius is the square root of 2. And our theta is 45 degrees. All right, so this here, 1 plus I to the 5th is the same as square root of 2 cis 45 degrees to the 5th. So the square root of 2 times a thing raised to the 5th power, we're still going to get the square root of 2 to the 5th power. And that's that r to the n in the notation up there. So like the first part of this does exactly as we would expect numbers to do. Over here, cis 45 added to itself 5 times is 5 times 45. All right, so 2 to the 5th is 32, which is 2 times 16. So we are going to have 4 times the square root of 2. All right, and then our cis 4 times 45, that's pi over 4. 5 pi over 4 is 225, but that's our quadrant 3 45 angle. So here I'm going to go back to 225. I sine 225. All right, and then since they gave us the problem in rectangular form, we should provide the answer in the same form. And normally 2 conversions is like extra busy work, but here it's way better than doing a FOIL 4 times, where you get increasingly more terms. Yeah, it's ugly. So both of these are -2 square root of 2. Sorry, negative square root of 2 over 2. I think I said it wrong, sorry. And then we just distribute through. So the 4 divided by 2 would be 2 times -2 from the radicals. And then it'll do the same thing again, just with an I. So that is -4 minus 4i, -4 minus 4i. So this number raised to the 5th power, we got this other strictly normal looking complex number. So we took that 1 plus I, multiplied it by itself 5 times, and we just end up somewhere in quadrant 3, a little bit further away. Now our nth root, due to the periodic nature of polar and the angles, like how they repeat, the sines and the cosines repeat themselves after a while, when we are looking for the root of a complex number, what we are looking for is a number raised to that n power would equal the number in question. So we're going to do backwards what we just did with de Moivre's theorem for the powers. Instead of raising it to the n power, raising it to the 1 over n power. And then instead of multiplying by n, we're dividing by n. But when we find the third root, or you know how like when we do a square root, we get plus or minus? There's 2 numbers that would square to the original polar. When we have cube roots, there's 3 numbers. When we have 4th roots, there's going to be 4 numbers. And what's interestingly is if you plot these, they're all actually, they all have the same radius and they're equally split around a circle. So our 4th roots, we're going to get like a quadrant 1, quadrant 2, quadrant 3, quadrant 4. All right, so this 2k pi over n, k starts at 0, 1, 2, 3, n minus 1. So since we're finding the 4th roots, our n is 4. So we are going to use k values 0, 1, 2, and 3. So we are going to have 1, 2, 3, 4 answers, which is why it says find the 4 4th roots. And there are some like weird tangential, strange like applications to this. It kind of crops up in unexpected places mathematically. I'm not sure what the outside math applications would be, but I'm pretty sure there are some. I'm just not familiar with them. All right, so, well, we have our 16. And the good news is 16 is actually 2 to the 4th. So our 1/4 power is actually going to work nicely. All right, so let's go ahead and follow our thing. So we are finding the 4th root So that is 16 to the 1/4 times the cosine of our theta is 120 over n is 4 plus 2k. Well, they put pi. So instead of the 2 pi, we can also do 360k over 4. Because remember, 2 pi radians is the same as 360 degrees. Since our 120 was degrees, I figured we'll just stick with degrees. Okay. So let's clean up some of these numbers. Oh, please don't crash again. Old computer. All right, so this the 16 to the 1/4. Like I said, 16 is 2 to the 4th. and then power to a power, they multiply. So that is just going to be 2. $120 divided by 4 is 30, plus 360 over 4 is 90. And yes, I technically should be writing degrees on all of those, but it's tedious. All right. So remember, there are 4 roots. So our first root is basically that. It's 2 cosine of 30 plus I sine of 30. And this is what we get if we make k equals 0. Now we're just going to go through the other 3 k values, 1, 2, and 3. All right, so if k is 1, 30 plus 90 is 120. So it is still the same 2, but it would be cosine 120 plus I sine 120. So this is the second number when raised to the 4th power, gets us back to our original. Our third root, still the 2, cosine, it's 120 plus 90, which is 210. And then for our k equals 3, 210 plus 90 is 300. So the fourth answer is 2 times the cosine of 300 degrees plus I sine 300 degrees. Now we could actually work out what each of those are. They're all on the unit circle. So these are going to be different, like square root numbers or halves or whatever. Just when we raise it to the 4th power, all the stuff will combine and cancel and get us back to that original 16 cosine 120 plus I sine 120. So there are some of the weird, cool things that complex polar notation does. I wish I knew where else we used it. All right, that is it for our little tiny toe dip into complex polar notation. Just enough so you can say, yes, I saw that once upon a time.